nodes, which are trying to maintain a consistent ledger of events, some of whom may be corrupt. Okay, so we want to ensure that these corrupt nodes cannot prevent the honest participants from maintaining a consistent ledger with one another. These events could be financial transactions, or just like recordings of, let's say, regulatory event or something like that. And the key is that we want to ensure we want to build such a system that can satisfy various properties. So what kind of properties do we want? Well, first and foremost, we want security. Okay, so we want to ensure that we can be robust to these misbehaving nodes. In addition to that, we want performance. So we want to be able to confirm many events per unit time with low latency. And this is particularly important in cryptocurrencies, which have been one of the main applications of blockchain so far. But it also matters in other applications as well. Some other properties, which are maybe second order to security and performance, include privacy and fairness. And the question that we want to ask as designers of blockchain systems is, how do we ensure that these properties are satisfied? Now, the classical approach to this in the blockchain literature has been to design algorithms at the application layer. So typically these will use tools from like classical distributed systems or applied cryptography to try to ensure that these properties all hold. However, the point that I would like to emphasize in this talk is that blockchains run on peer-to-peer communication networks. And these networks have a huge impact on the properties of blockchains in general. So it makes sense to think about these networks as we are designing our blockchain systems. So this whole talk is going to be about asking, how can we incorporate the peer-to-peer network into the design of blockchains to get better downstream performance for these properties that I mentioned earlier. So in particular, I'm going to focus on three separate sections of this talk. The first will focus on performance, and this goes hand in hand with security because you don't want one without the other. Second part will focus on privacy, and the third part will focus on fairness. We'll very briefly touch on this. And for all of these, we want to talk about different ways in which we can incorporate knowledge of the peer-to-peer network. So at the most basic level, this involves just modeling what is the network doing and and analyzing how does that affect the downstream algorithms. And on top of that, we can also think about how do we actually redesign the peer-to-peer network to better support these downstream properties that we want to enforce. Okay, so I'll show a couple of examples of how to do this in various areas. So I want to start with a brief primer on how blockchains work. Okay, so let's start out by talking about the Bitcoin peer-to-peer layer. So Bitcoin is not the only blockchain, but it is the first one. And a lot of successive blockchain designs look very similar to Bitcoin. So I'm just going to use this as our canonical example. Now in Bitcoin, nodes are connected to one another in a peer-to-peer network of TCP links. Okay, so here each coin represents a node. And a node is just a device that's running the Bitcoin client software. Now, users of this network, like Alice and Bob, have multiple identities. First identity that they have is a public key that identifies them. Okay. In addition to that, transactions have public keys that identify them as well. So if a user, Alice, wants to send money to another user, Bob, the first thing that she does is to compose a transaction in plain text that says Alice, identified by her public key, sends money to Bob, identified by their public keys respectively. Okay. So this transaction message is sent in plain text over the network until all of the other nodes have seen this transaction. Okay, so now we all know about it. How do we actually all come to agreement that this transaction is valid? This is where the consensus protocol comes in, which is called Nakamoto consensus or longest chain rule. So the idea here is that once Alice generates her transaction and sends it to all of her peers, a subset of these peers, who are known as miners, are going to start racing to produce blocks. What does that mean? So each of these miners is trying to solve a computational puzzle, a random computational puzzle, and their probability of solving that puzzle first is proportional to the amount of computation or hash power that they have in the system. Okay. So let's say one of these guys wins this, solves the computational puzzle first. Basically, they're brute forcing a hash function. So let's say one of them solves this puzzle first. That allows them to produce a block, which is a data structure containing both the transactions that have been recently proposed and a pointer to a parent block in the overall blockchain data structure. So here the parent is this Genesis block, their original block. So once that happens, this process starts over again. Now they solve another puzzle with the successive transactions in the system. And one of the key insights of Nakamoto consensus is that because this is a distributed system, different users may, for various reasons, propose blocks that are both pointing to the same parent, okay, like we have here. And in this case, as the name suggests, the longest chain rule, Nakamoto consensus says that you'll always build on the longest chain that's visible to you, okay, which means we're going to ignore this branch on the right, and future miners are going to, honest miners are going to continue building on this longest chain. Okay, so we're almost there. So if I'm a user of this system, I'm going to treat my transaction, or Alice is this red node. Alice is going to treat her transaction as confirmed once the transaction is embedded in a sequence of k blocks in the longest chain. Okay, so once we have k successive blocks, all of which are pointing transitively to my transaction, then we consider this transaction confirmed. Okay. Now, k here is chosen as a function of our desired reliability, epsilon. Okay, so what is reliability? Reliability means that as long as less than half of the nodes are corrupt, or rather less than half of the hash power in the system belongs to corrupt nodes, then a transaction cannot be reversed except with probability at most epsilon. Okay, so epsilon you should think of as like a probability of a transaction getting reversed after this k confirmation rule says it should be good. Okay, and so this number k should be growing roughly as like log 1 over epsilon. So it's growing. It's growing with epsilon. And different users can choose different reliabilities that they want to operate at. Okay, so this explains, first of all, the kind of life cycle from when Alice first proposes her transaction to when she finally decides that the transaction has been accepted by the rest of the system. Now, why is this k confirmation rule secure? To understand this, we can think about the adversary and the honest miners as basically two Poisson processes. Okay? So each one of these parties is trying to generate blocks according to a Poisson process whose rate depends on the fraction of total computation that they have in the system. Okay, so the honest party is producing blocks at one rate, which is faster than the rate at which the adversary is producing blocks. And the key insight here is that in order for the adversary to overtake or to reverse an honest transaction, they need to produce a longer chain than what the honest guys have. Okay? And by the law of large numbers, we know that as time increases, the total fraction of adversarial blocks is going to concentrate around beta, the fraction of hash power that they own. Okay? So what this means operationally is that we choose a k, an embedding rule, such that with high probability, a probability that we control, the adversary cannot generate enough blocks to overtake the honest chain. So this is the intuition about why K confirmation rule is secure in Bitcoin, in a Nakamoto consensus. Okay, so what does the P2P network have to do with all of this? Well, the P2P network is governing the dissemination of both transactions and blocks. And so if this breaks down, basically all of our security guarantees disappear. So this dissemination process is currently well modeled by a diffusion process, meaning if we have some red node here that starts broadcasting its transaction or its block, on each of the adjacent edges, it will spread that transaction or block with a delay that is distributed exponentially with some parameter lambda that depends on both the code base that you're working with and the hardware and some other constraints that I won't go into. So the idea here is that as your transaction spreads, on each of the adjacent edges to this like red region, the message, due to the memorylessness of exponential random variables, the delay on each of these edges is again going to be exponentially distributed. Yes, and so we call this a diffusion process, and it has been widely studied in this community in particular. And we're going to see how this diffusion process affects properties like performance, privacy, and fairness. Okay, so let's start by thinking about performance. So this section is going to be based on a number of papers. In particular, I'm going to focus on the two recent ones in red. And here we're going to start by thinking about how do we actually evaluate the performance of a blockchain. So right now there's a literal zoo of different consensus mechanisms that people have proposed, and all of them have different trade-offs in terms of two main performance metrics. The first one is confirmation latency, and the second one is transaction throughput. So here on this plot, we want to be lower, so we want to have lower latency, and we want to be further to the right, so we want higher transaction throughput. Now, there's some fundamental limits that we just can't exceed. So on the latency side, we can't go faster than the speed of light delay. So this is the delay it takes to transmit a transaction from one node to everyone else in the network. So this is going to be a lower bound on our latency that we can achieve. We also simultaneously have an upper bound on transaction throughput that's governed by the capacity of our network. So we define this as the number of transactions per second that our network can reliably transmit to the rest of the nodes in the network. Okay. So ideally, we would like to be at this yellow point, right? And the question that we set out to answer in this work is how close can you actually get to this yellow point? So as we started thinking about this question, we wanted to model the peer-to-peer network, but in a way that's a little bit more coarse-grained than what I mentioned earlier, specifically with regards to that diffusion model that we talked about. So we have this broadcast network that's used to flood blocks and transactions over the network, and we decided to model this as follows. So we have our network capacity C, which again is the number of transactions per second that the network can reliably transmit. And we have D, which is our speed of light propagation delay. Now we're going to model the overall delay of transmitting a block over the peer-to-peer network as follows. So we have two terms here. The first is our propagation delay. Okay, so this is a lower bound, so it gets added to the overall delay. But the second term here is something that depends linearly on the size of our block. And this is in terms of the number of transactions per block. Okay. So what is this saying? This is saying as you're trying to send larger and larger blocks, it's going to take more and more time to actually transmit that block to all of the other peers. And this gets divided by the capacity of the network. Okay. So this network delay model is actually informed by some prior work that actually took measurements of the Bitcoin peer-to-peer network and observed this phenomenon that larger blocks take more time to propagate, and the relation with block size is actually linear. So here we've taken kind of an abstraction, an end-to-end abstraction of the peer-to-peer network and used it to model the overall delay of blocks in the system. Okay, so just to summarize, our model has a few different components. So for the network, we're modeling the delay just as I just explained. We're modeling an adversary who controls a fraction beta of the computational power in the system. Okay, and beta here has to be less than half. Adversaries do not need to follow protocol, and they can also communicate instantly among their nodes. Now, in parallel, we're mining blocks according to a Poisson process. And this is actually a very good model for how blocks are mined today in the Bitcoin network. So this is one case where modeling as a Poisson process is actually not a stretch. So we model blocks being mined as a Poisson process with rate proportional to the fraction of computational power. So if we're mining at a total rate of f blocks per second, the adversary is mining at a rate of beta f, total blocks per second. Okay, and then confirmation is defined as an event where the transaction cannot be reverted with probability more than epsilon. And this is worst case over all adversarial actions. Okay, so this is our model. Let's think now about what are the fundamental limits that we can hope to achieve. So I touched on this a little bit earlier, but if we look a little closer at throughput, for example, we can see that as our adversarial fraction beta varies from 0 to 0.5, our throughput must also decline. Okay, so clearly we can't do better than our network capacity C. But in addition, as you get more and more adversarial nodes, you also can't force the adversary to contribute to your throughput. So your total throughput has to be upper bounded by this curve. Okay, at the same time, if we look at latency now as a function of our reliability, epsilon, as we said before, this is going to be lower bounded by the speed of light delay, d. Okay, so our goal here is to operate in these gray regions, and we want to come as close as we can to the black lines, to the fundamental limits. Okay, so how do we do that? Well, the key insight is that in Bitcoin, blocks play two roles. The first role, which we talked about earlier, is adding transactions to blocks. So anytime Alice produces a transaction, blocks are the vehicle through which that transaction gets added to the blockchain. But the second kind of implicit role that blocks are also playing is to vote on other blocks. So every time, for example, I add a block to this chain, to this longest chain, my block is implicitly saying, I believe that all of the previous blocks in this chain are valid, and I'm affirming that. And that's the sense in which K confirmation is effective. Like these K blocks that we're adding are like K votes for a particular transaction that you're trying to confirm. Okay, so Nakamoto consensus has tied these two roles together into one object. How does that affect us in terms of performance specifically? Well, it affects us in two ways. The first is that in Bitcoin, due to security concerns, which I'll mention in a second, the mining rate has to be very slow. Okay, so we're mining blocks at about 1 block every 10 minutes, okay, which is really slow. And this low mining rate means that we're also adding transactions very slowly to our blockchain. And adding transactions slowly means that we must have low throughput. Okay. At the same time, the other function that we talked about was voting. Now, again, because we have a low mining rate, that means we also have a low voting rate, which means it takes a long time to get K votes on your transaction, which means you have high latency. Okay, so this low mining rate is really causing problems for us. It's hurting our throughput and our latency. So a natural question to ask here is, why can't we just increase our mining rate? So now all of our miners, our honest nodes, are going to produce more blocks per second. Some of those blocks may conflict with one another, so they may appear at the same level, but that should be fine. So why can't we do that? The problem is that as we increase the mining rate, it also increases for the adversary. And now the honest nodes have this kind of overlapping structure. As we increase the mining rate, we get more forking, or in other words, we get more blocks at the same level. But the adversary is able to communicate instantaneously, which means it can take its additional blocks that it's mined and it can line them all up into one chain and create the longest chain in the system, while the honest nodes are struggling to resolve conflicts in their tree that's getting wider and wider. So increasing mining rate actually trades off efficiency for security, which is not a trade-off that we want to make. So actually, if you look at the trade-off curves that we showed earlier, and we plot Bitcoin on here, so here I'm varying the adversarial fraction, we can see that Bitcoin actually is pretty far away from our upper bound on throughput. And actually the operating point that they're using today is this red dot down here. So they're trying to be robust to around 49% adversarial nodes, which means that the throughput that they're actually able to achieve is very far away from this upper bound. At the same time, the latency is also terrible because, as I mentioned earlier, the depth, our confirmation depth, K, has to increase exponentially in epsilon. Okay. So this means that our latency here is growing with a slope of that looks like O of D, where D was our speed of light propagation delay. Okay, so we're very far away from the lower bound on latency and the upper bound on throughput. So what can we do to fix this problem? So the idea that we explored in this work was to actually separate these two roles that blocks play into different components that can be manipulated independently of one another. So in particular, we separated the role of blocks into one component that maps transactions into blocks, and a separate component that takes blocks and uses that to generate a consistent ledger. And the way we did that was by producing different types of blocks. So so the first type of block that we produce is called transaction blocks. So these are blocks that just take transactions and put them into a data structure. And these transaction blocks can be produced really quickly. And that's done to improve our transaction throughput. The second type of block that we have is called proposer blocks. And these are built up in what's called the proposer tree. So here, the proposer tree is basically its own separate blockchain that is pointing, where each block is pointing to one parent in the proposer tree and to some subset of these transaction blocks. And the pointers to the transaction blocks are really just saying, okay, I believe this is a valid transaction. Okay, again, like before, because of various conflicts, it's possible to have multiple proposer blocks at the same level. But we're going to talk in just a second about how we resolve those conflicts. Okay. All right, so here we have our proposer tree and our transaction blocks. Now, the key question is, how do we finalize a sequence of these proposer blocks? The way that we did this is with what we call voter trees. Okay, so here we're going to have a huge number of independent blockchains, which we call voter trees. So like, think 1,000. So we're going to have 1,000 of these separate blockchains, each of which is supposed to vote on proposer blocks. Okay, so and specifically, the rule here is that our voter trees have, each voter tree casts one vote per level on the proposer tree. So here, for example, at level 1, we have only one proposer block. So all of the voter trees are going to vote for that one block. However, at level 2, we have two possible proposer blocks. So now the voter trees need to choose which one of those they think is valid. So let's suppose two of these trees vote for the block on the right, and one votes for the block on the left. In the end, we're going to pick something that looks like a majority vote, and I'll explain in a little more detail next how we do this. Okay, and then once again, at the third level, we have only one block, so everyone votes for the same block. Now, each of these voter trees is growing according to the longest chain rule. And accordingly, they have to grow slowly because Nakamoto consensus is only secure when you're adding blocks very slowly. So basically what we have here is 1,000 slowly growing voter trees, each of which is trying to pick which proposer block at a given level is the correct one. Okay. So why, this is kind of complicated. Why are we going through all of this? I think the next slide will hopefully make this clear. So the next slide tells us our confirmation rule. So as I mentioned earlier, in the case of level 1, we only had one proposer block, and so all of the voter trees voted for this one block. Now at level 2, we have a decision to make. Do we choose block A or B? Now, the reason that we need to choose one of these is because we need a consistent sequence of events. Otherwise, it could end up that you keep adding more and more blocks at a given level. So we need to choose one and be able to finalize that and move on with our lives. So basically what we want, the kind of rule that we're looking for here is we want some condition after which we can conclusively say that we're going to choose either block B or block A. So a naive way of doing this would be to collect the votes from each of these trees and then wait for those votes to get confirmed with a K-deep rule. But the problem here is that if we do that, remember I said that each of these voter trees is growing very slowly because it has to, because it's using the longest chain rule. So if we did that, that would actually not give us any latency gains at all over Bitcoin. So what we do instead is to observe that we don't actually need to wait for each of these trees to get finalized. What we could do instead is to only confirm each of these trees with low confidence, but rely on the fact that we have lots of them, because all we care about is the sum of the votes. We're not too worried if one individual tree flips, as long as the majority vote doesn't flip. Okay. So basically what we're doing here is computing confidence intervals over each of the, over the number of votes to block A, to block B, and to some potentially hidden, like as yet unseen block that could arise. And once those confidence intervals get tight enough, and we can confirm that with high probability, block B will remain the winner of this race, then we can say, okay, we think block B is the winner here. Okay, so this is like, once again, using the law of large numbers to try to get around the latency limits of longest chain consensus. So that's I think the key insight for improving the latency of Bitcoin. So if we go back to our initial results, we can see here we had our upper bound and Bitcoin was down here, and Prism is actually able to achieve within a constant factor of this upper bound. And moreover, if we look at this latency plot from earlier, we can see that Prism is able to maintain a latency that scales as order D, or speed of light propagation delay, for a much broader range of error probabilities. So in particular, it remains order D until we hit basically the bandwidth delay product of our network. And after that, the slope starts increasing at a slope that looks like 1/c, our capacity. And this slope is going to be quite small because these capacities are big in practice, like 100 Mbps, for example. Okay, so theoretically, Prism seems to achieve much better throughput and latency compared to Bitcoin. And in fact, our main result is that if the adversarial power beta is less than 1/2 and reliability epsilon is exponentially small in the bandwidth delay product, then Prism is guaranteed to confirm honest transactions with a latency proportional to D and eventually confirm all transactions. It also achieves order optimal throughput proportional to 1 minus beta times C. Okay, so very quickly, the key idea here is to use basically a union bound over these voter trees. So we need to ensure that each individual voter tree has a large enough probability of being permanent. And once we have that, we can rely on the fact that we have many of these trees to bound the probability that the majority vote is going to flip. So these proof techniques look fairly similar to other prior analysis of Bitcoin, with the key difference that we now have a lot more moving parts that we need to keep track of. Okay, and these gains are not just theoretical either. So we implemented Prism in Rust, and this figure shows the performance benefits as we move from Bitcoin to Prism. So here we see the trade-off curve as we change the mining rate for Bitcoin. We see that as we increase our mining rate, our throughput gets better, but at the expense of latency, because we need to preserve the same security level. Whereas Prism is giving us much higher throughput and much lower latency. So in particular, we're getting 10,000x better throughput than Bitcoin, and latency that's about over 100x better than Bitcoin. So kind of the take-home message here is that by modeling and analyzing the network more carefully, we were able to see performance bounds that were not previously explicitly characterized. And it also allows us to design protocols that can account for these real network dynamics, both in theory and in practice. One downside is that this protocol is a lot more complex than the Nakamoto consensus. So this is, I think, one of the key weaknesses of Prism compared to other baselines. Okay, so that's the first part of the talk, how to incorporate the P2P network into designing more performant blockchains. So before I move on, I wanted to ask if there are any questions.
Varun, you can go ahead and ask your question in the chat box.
Giulia, like a quick question. So I know that you were keeping the network capacity the same. Are you also keeping the hashing power the same? Because in these other trees that you're building, it seems you may be wasting hashing capacity because they're you have so many of them and they're sort of mining blocks, but you're only using few of them. So is that also kept the same across the two comparisons?
That is also kept the same. Yes, that's right. So yeah, so previously, yeah, so like for Bitcoin, let's see, hang on, let me just pull up. Okay, yeah, so for Bitcoin, all of your hash power would go towards building basically the single main chain. But the idea is that now we've split all of that hash power, we're subdividing it into different types of trees. So for example, let's just ignore the proposer tree and the transaction blocks. If we just think about the voter trees, each voter tree has 1/1000th of the total hash power that the main chain on Bitcoin would have had. And the way that we ensure that that's respected is through some cryptographic tricks that I didn't mention.
Like one more quick follow-up. Do you know, like, if you just increase the block size, what's the trade-off? Like, that's one more thing people have proposed, right, for increasing the throughput?
Yeah, good question. So if you just increase the block size, the problem is that it also increases your latency. So you can use that to improve your throughput, but it comes at the expense of both security and latency, because it now takes longer to broadcast the block over the network.
I have maybe a naive question, but for this longest chain rule, are the honest agents also potentially confused by the the dishonest ones? As in, if like, do I need to make sure that the malicious chain does at any time point never exceeds the length, or if at one time point it exceeds the length, would the honest people accidentally start to build on the malicious chain?
Yeah, so if at any point the publicly visible tree has a longer branch, which might belong to the adversary, the honest miners will switch over to that longer branch.
I see. So you need to show this dominance over every time point.
Yes. So the point here is that even with that property, okay, hang on, sorry. I see. Yeah, I see what you're asking. Yes. Yeah, you need to show it for all time points. So you can say after this point in time, you're guaranteed that at no future time point will the adversary be able to create a longer chain, except with probability at most epsilon. Was that your question?
Yeah.
Okay.
And in this diagram, the proposer blocks, are they also slow, or are these?
They're also slow. Yeah. So the only ones that are fast here are the transaction blocks. But the key is we only need to wait for like one proposer block to get built instead of K of them.
So to follow up on Christina's question, if a short stretch of blocks by the adversary gets longer, is it only those blocks that will, I mean, are you just accepting a certain number of wrong transactions and then the rest of your transactions are okay?
So good question. So what can happen is if the adversary is able to overtake the main chain for a short period of time, the honest nodes will switch to that main chain, to that adversarial chain, only if all of the transactions are consistent with each other. So if the adversary proposed a longer chain with like junk transactions that are just producing money out of thin air, the honest nodes would not accept that as a valid longer chain. The condition, which I should have mentioned earlier, is that they first validate that each one of those transactions is globally consistent with the entire history of the chain, tracing from that longest one back to the Genesis block. So they would not, so I think this is one of the things that kind of confused me when I first started thinking about this space. There's no such thing as like a right transaction and a wrong transaction in a distributed system. You just need all of the ones that everyone agrees on to be consistent with one another. Now, from the standpoint of like a merchant and a vendor, maybe you feel differently, but from the standpoint of designing one of these systems, the validators, the nodes that are participating in consensus just need to make sure that everything is consistent, is self-consistent.
Okay, but it could be consistent with a small proportion of fake transactions that didn't happen. So
it needs to be consistent with all of the previously recorded transactions in that chain. So for example, let me go back here. Let's see. Okay, so for example, in this picture, let's suppose that actually, this isn't a very good one. Let me go back to this picture. Okay, so let's suppose that we had three blocks on the honest chain, and then the adversary releases their longer red chain. And let's suppose we have some transactions that are stored here in the Genesis block. All of the transactions in this red chain must be consistent both with each other, with a sequence of transactions in the red chain, and with the transactions that were in the Genesis block. If they now, so the fact that they get recorded means that they do exist, because the transfer of money in cryptocurrencies is governed entirely by what is present on the public blockchain and that everyone agrees on. So for example, if, and this, I see what you're asking. So the adversary here can't make up fake transactions that didn't happen, because each transaction here has to be cryptographically signed. So here, our transaction, all of this is signed by digital signature using the private key of Alice. So the adversary can't just make up transactions out of thin air and get them accepted by the honest nodes.
Okay, thanks. I think that's what I was getting at.
Okay, sorry. Any other questions?
So I have a follow-up question on that. Then if adversarial nodes can't create these fake transactions and make money out of thin air, then what kind of attacks are we looking at here exactly?
So the kind of attacks that we're looking at is where an adversary creates a transaction that is conflicting with something that happened in the main chain. So for example, let's suppose that here in the main chain, let's say our adversary goes to the store and tries to buy a car with Bitcoins. Okay, so this transaction, let's see, can you see my cursor? So this transaction here represents the adversary paying, 1 Bitcoin for a car. Now, the car dealer waits for K blocks for this transaction to become confirmed. And now the adversary says, okay, I'm going to get this car for free. I have the car now. So what I'm going to do is release K+1 adversarial blocks in which I pay that same money to myself, not to the car dealer. So adversaries can create transactions that conflict with a transaction on the other branch, but that are still self-consistent with the entire history of the branch that they're building on. Does that make sense?
That makes sense. Yeah. Thanks.
Any other questions? Okay. Cool. So let's see, I have, okay, not a lot of time. So I'm not going to spend too much time on this, on the latter two portions of this. But I wanted to briefly mention some similar cases where we can take, where we can model and think about the peer-to-peer communication network to provide other properties like privacy or fairness. Okay, so on the privacy side, remember we had this figure and we said that users have multiple identities, like they have a public key and they also have an IP address for the nodes that they're running. So when we think about privacy in blockchains, typically there's two variants of privacy that we think about. First is at the application layer. So here, the idea is that we want to ensure that a transaction cannot be linked to Alice's human identity. And this has been the bulk of the focus of research in this space. So typically it uses the public blockchain to try to link together transactions from the same human and uses that to maybe figure out what is the identity of that human. But there's also privacy implications at the network layer, meaning that an adversary might be able to link this same transaction to Alice's IP address, which gets us part of the way to actually figuring out that this transaction belonged to Alice. So, so this problem is actually really related to a set of literature that has come out of this community, the SNAPP community. And the idea here is that if we have an adversary that it has placed itself within the peer-to-peer network, so let's say, for example, we have a fraction P of spy nodes in our network. And these spies, their identities are unknown, and they observe all metadata, and they can collude with one another to try to infer the source of a particular transaction. Then that can be used to actually break network privacy. So this becomes a problem of source inference. So if a transaction starts at this blue node and starts spreading according to this diffusion process we mentioned earlier, these spies are able to collect timestamps about when they saw the transaction and from whom they received it. And there's been a lot of work showing that under various models, diffusion spreading can be de-anonymized in the sense that this botnet adversary can infer the source of the diffusion process reliably. And what reliably means depends on the adversarial model and the details of the diffusion process. But there's been a lot of work across different models showing this kind of result. So what we tried to ask in this work was, can we actually change the spreading, the peer-to-peer flooding process to make this more privacy preserving? So in particular, we extended previous work on this by adding another metric for anonymity. So here we assume that we have some number of transactions and some number of users. Sorry, what? I have like 10 minutes. Okay. Some number of transactions and some number of users. And the adversary is trying to design a mapping from transactions to users that maximizes their recall. So in other words, this is just the probability of mapping a transaction to the correct user, while also maximizing precision. Okay, so here, this is just saying if you map all of your transactions to the same user, that's not a good mapping. So the adversary is both trying to maximize the probability of detection and maximize, in some sense, the spread of its mapping across different users. Okay. So our goal was to design a distributed flooding protocol that minimizes the maximum precision and recall that can be achieved by a computationally unbounded adversary. And so we started by showing some fundamental limits on precision and recall. And these limits look kind of funny if you've worked with precision and recall before as metrics. But the reason is that we assumed here that each user has one transaction. So there's n users and n transactions. And as a result, if you have high precision, you also have to have high recall, and vice versa. So that's why precision and recall must lie within this kind of almond-shaped region. And what we found, and so if you fix a particular spreading mechanism, let's say diffusion, the adversary can choose different estimators or different algorithms for picking this mapping. And these different estimators are all going to achieve different points or different regions on this curve. So we call this region for a particular spreading mechanism an achievability region. So basically the adversary can achieve anything within this outlined region. And our goal is to make that region basically as small as possible because we want to minimize precision and recall. So we showed some lower bounds on both the precision and the recall that depend on P, the fraction of adversarial nodes in this network. And these bounds imply that the best region you can hope for is this little green triangle. So we want to design a spreading protocol that achieves the green triangle. So our attempt at this was a protocol called Dandelion, which basically, instead of launching a diffusion process that spreads symmetrically in all directions, it's going to spread content asymmetrically. So if our source node is this guy here on the left, it's going to start passing the message over, not in all directions, but just over one of its neighboring edges. And it does this for a random number of hops until finally it starts diffusing the message. So we call this the anonymity phase and the spreading phase. Kind of looks like a dandelion seed head. But the point here is that dandelion spreading is useful for us because it has an optimally low maximum recall. So it meets our, so plus smaller order terms, it meets our lower bound of P on the maximum recall that can be achieved. Now this holds for any graph topology, but in addition, to actually get the good performance with respect to precision as well, we need to change the topology of our peer-to-peer network actually. So what this means is that the stem of our dandelion is always going to be propagating over effectively a cycle graph. Okay? So if a transaction 1, TX1, comes in at this node, it's going to propagate for a random number of hops over this black anonymity graph, which is a cycle, until it starts the spreading phase. And then it starts diffusing over the regular peer-to-peer edges. Similarly, if a second transaction comes in, here tx2, it's going to propagate clockwise over this same anonymity graph for a random number of hops until it starts diffusing as well. Okay, so we have kind of two components. One is that we use this dandelion spreading, and the other is that we change the topology of our graph, of our peer-to-peer network, to actually look like a cycle. And you can show that under these conditions, Dandelion has a nearly optimal maximum precision. So here by nearly optimal, I mean within a log factor of our lower bound, p squared. And so if we go back to this achievable region from earlier, so remember the green triangle is what we wanted to achieve. So we can see that Dandelion hits the recall upper bound and is within a log factor of the precision bound. Whereas diffusion, which is what's done today in many existing cryptocurrencies, has a much larger region. So it's worse for privacy. Okay, so for the sake of time, I'm just going to skip this slide. So we did, actually, no, this is kind of interesting, I think. So why is this a good idea? To illustrate this point, I want to give you two examples of graph topologies that don't work well. Okay, so the first one is a tree. So let's suppose we have a tree where all of our leaves are sending messages up to the root, and then the root is going to diffuse. This has bad precision. This is a precision of O of p, whereas our lower bound is O of p squared. And the reason is that each one of these SPI nodes in the second to last layer is able to perfectly de-anonymize the nodes that send messages to it. And the problem is that we have a linear number of SPI nodes in the second to last layer, which is why we get this precision that scales linearly in P. So the message here is that if you have too many leaves, or rather too many nodes that are connected to leaves, then you're going to have bad precision. The second class of graphs that also doesn't work well, and this was kind of surprising to us, is complete graphs. So here, the problem is that you just have too many paths on this graph. So in order to get good precision, you want lots of different transactions to traverse the same path in the network. Whereas on a complete graph, you have so many edges that the probability of two transactions taking the same path is actually really low. So the problem here is that we have too many paths. And so cycle graphs are a nice compromise here. So they don't have any leaves, and there's only one path that transactions can take within the graph. So that's intuitively why a cycle graph is the right thing to do for this privacy problem. Okay, and Dandelion is, in terms of its privacy guarantees, it's weaker than a lot of the cryptographic approaches that people have proposed. But what we've seen in practice is that a lot of complex cryptography tools actually don't get really deployed that much in practice, just because they require a lot of expertise to deploy. So in line with that message, we've seen Dandelion has been implemented in a number of cryptocurrencies, including Monero, which is one of the big ones. And it's being considered for a few others, including Zcash and Bitcoin. Okay, so that's that's what I wanted to say about privacy. I'll just spend like 2 minutes on fairness for the sake of time. So the problem with fairness is that front running is a big issue in blockchains. So the idea is that miners or users of distributed financial systems can use observations of each other's transactions to try to basically game the system. So get in buy orders before somebody else does in order to cause the price to go up and then sell later. So this is a very common game in traditional financial systems, and it's a big problem. The SEC heavily regulates front running in classical financial systems. But the problem is that in cryptocurrencies, we have basically a Wild West. It's very difficult to regulate this kind of thing. So this, again, ends up being a peer-to-peer network problem, because if your front runner is located between a victim and a miner, then the frontrunner can generate transactions that are messing with the order in which transactions are processed by the miner. So we've started very recently looking at questions related to how can frontrunners manipulate the structure of the peer-to-peer network to improve their chances of success. And this leads to some interesting graph problems related to like topology modification and analyzing the speeds at which transactions reach a particular target in the network under these modifications. Okay, so all right, so for the sake of time, I'll wrap up there. So the take-home messages here are, first of all, that the communication network plays a very central role in designing public blockchains. And this role hasn't been as explored as I think it should be. And actually, thinking about the role that this network plays can lead to pretty substantial gains in various properties that we might care about in our blockchain systems. So I showed some examples of that for performance with Prism and privacy, Dandelion, and I didn't really talk about fairness, but gave you some idea of what the kind of open questions are. So with that, thank you all so much for your attention, and I'll be happy to take any questions.
Thanks, Giulia, for a great talk. I'll clap on behalf of everyone. And yeah, open to questions. Feel free to unmute yourself directly to ask. Varun, you can go first. Oh, wait, sorry, that was a clap, not a question. Okay, so anyone who wants to ask, feel free to unmute yourself.
I had a question on the more the mathematical fundamental part of the analysis. Mm-hmm. So in the beginning, one of the assumptions was the Poisson arrival process of block, or that mining blocks follows the Poisson process. Mm-hmm. But there has been some literature lately that argues against this based on Bitcoin data. And for most of the things that you, or at least in analysis that we did, we saw that the data was relatively robust. So the Poisson, it was not, let's say, one-on-one Poisson, but the results that we want to use, for example, the law of large numbers, that worked still fine in practice. But do you think that in your analysis that this plays a role, or that this also, your model is also robust to small errors in the Poisson assumption?
I see. So sorry, I'm actually not familiar with this work. What's the main conclusion? I mean,
so what I did is a data analysis. So it's a data analysis on blockchain of Bitcoin block data. I can also link the article.
That would be great. Thank you.
And they see that it's not a homogeneous Poisson process, but they argue some type of time-dependent.
I see. So are they arguing that locally it's still a Poisson process, but the rates change over time, or?
Yeah, something like that. Yeah.
I see. That should, well, so it all depends on the rate at which the rate is changing. So I think my guess is that let's see. So I guess this is going to be governed by the rate at which miners are joining and leaving the network.
Yeah, because it resets every 2,000 blocks or something like that.
Right. So yeah, like Bitcoin has this self-adjusting mechanism where it tries to keep the rate as constant as possible. So I could see this causing a problem depending on how quickly these rates are fluctuating. And when I say causing a problem, I mean in terms of the guarantees that we're obtaining, because the guarantees do rely pretty heavily on the fact that it is a Poisson process of the same rate. So let's see, how do we change that? One thing you could potentially do is like split the analysis into phases. So like maybe we can say, or into epochs. So maybe we say like during this epoch, we have a certain rate. During this epoch, we have a different rate. It's not, I would have to think about it a little bit more, like what it would take to actually extend or like whether the same results would go through. I haven't thought about this at all, but that's a really interesting point. Thanks for bringing it up.
Yeah, thank you for your insights. This is also something that puzzled us. So I was wondering if you, what your opinion on the matter was.
This is also something that what?
That also we also were surprised by. There's a lot of literature that uses this assumption. So seeing an article that argues kind of hardly against it was also surprising to us.
I see. Yeah. Yeah, I mean, I think this is one of the challenges that arises from like minor arbitrage. So if it's easy to switch between different blockchains, between mining for different blockchains, it's actually, I guess, not super surprising that this would happen.
No.
So like if a miner can get more profit mining for Ethereum than they can for Bitcoin, they're going to switch. But I was not aware that people had done this kind of measurement. So thanks for mentioning that.
Okay. And maybe another question on this may be a little bit naive, but in the privacy part, you talk about these spy nodes.
Mm-hmm.
But what I can imagine if a spy node would go into the network, and it would make a lot of connections because it wants to spy on a lot of nodes.
Mm-hmm.
But that makes spy nodes by definition more special.
Yeah, that's it.
Is it possible to detect spy nodes based on this property?
So detecting spy nodes is actually difficult because you don't have much control on what they're going to do once they're connected. But you can make Dandelion somewhat robust to this by forcing the edges of that cycle to only be outbound edges. So basically in this peer-to-peer network, Bitcoin distinguishes between connections that I set up. So like if I connect to you, that's an outbound edge. Whereas if you connect to me, that's an inbound edge. So for this line topology, I'm only ever going to pass messages along outbound edges. So like if you generate a bunch of connections to most of the nodes, it won't actually affect the anonymity properties.
Okay. Okay. Thank you very much for the answers and the talk. It was very nice.
Thank you.
Giulia, I had maybe also a naive question about the Dandelion. So in terms of the network, like how much of the network structure are you able to control? Or are you suggesting that if the network structure is one that maybe is, like let's say it's a complete graph, even though there's too many paths, you can just have your protocol pass on a set of the edges so that it's not actually, so you're like choosing so that you can choose the network topology in some sense?
Yeah, it's the latter. So basically you can only choose your local connection. So no single node or no single entity has that much control over the topology. But what you can do is choose an overlay. So like if we go to like here, so let's suppose that like all of these edges were initially part of the network, but I'm going to choose some of my connections, in particular the outbound ones, to be special and to be part of this cycle graph.
I see. But your Dandelion, you need kind of both a long part, but also a diffusion part of it. So is it that you would differentiate which edges you use for the first stage versus which edges you use for the second stage?
Exactly. Yeah, that's how we do it.
Oh, I see.
Yeah, and the second part is really only needed for latency purposes. You just need to ensure that your transaction reaches the rest of the network quickly enough to get mined with some reasonable delay.
I see. So you just choose all the edges for the second part.
Yeah, exactly. That's right. Mm-hmm. Yeah, great questions. Anyone else?
I have a question about the p fraction of spice assumption.
Mm-hmm.
What is stopping an adversary from like creating as many nodes as he wants?
That's a good question. The answer is nothing. Well, okay, so there is some cost associated with spinning up more nodes, but it's actually like relatively cheap.
Mm-hmm.
So actually there were some instances recently of attackers trying to launch this kind of attack on, I want to say Monero. So like, sorry, no, it was Grin. It was Grin. So it's another cryptocurrency. So they tried launching a bunch of these spy nodes and they showed basically that they can do some kind of basic attack, which is still it's consistent with the results that we got, but just demonstrating it in practice caused kind of a stir in the community. So in principle, there is nothing preventing you from just spinning up a bunch of nodes. These are permissionless systems, and if you do, like, once you get P above 30%, your probability of detecting the source is actually pretty high.
Okay.
So this is more of like, if you think of it in terms of security, this is like putting a lock on your front door. It's not going to stop a determined attacker, but it stops random kids from entering your house.
But could there be a possibility of using something like proof of work for all participating nodes, which makes a civil attack unlikely?
Yeah, so people do. So I think the big industrial blockchains that people are building today are by and large permissioned. So either so basically they require you to be a known entity to actually have access to this kind of network traffic, and that's the way that they're dealing with it in industry today. So these problems relate primarily to permissionless blockchains like Bitcoin and Ethereum that are trying to open the doors to anyone who wants to enter the network, but has this related problem. Potentially, you could add some kind of requirement like what you're suggesting. I think it's a trade-off there between how accessible you want to be to the rest of the nodes versus how resistant you want to be to Sybil attacks.
Okay, thank you very much.
Thanks. Anyone else?
Okay, I think those are the questions. You're welcome to stay and chat longer as well. But thank you so much, Giulia, for a great talk. And
yeah, thank you all. Thanks for the great questions. This was fun. Okay. All right, and thanks, Christina and Wayna, for the invitation. This was fun.
Yeah, no, I really enjoyed your talk. Thanks for coming. Okay. And on a crazy weekend for you too.
Okay, cool. Roel, or how
Can
do
I
you
maybe ask? Sorry.
How do you pronounce your name?
Roel.